Hello all. Welcome to another video of the regression analysis course. So far we have learned how to estimate the parameters of a simple linear regression model using the ordinary least square estimation method. In this video, we'll explore a different method, one that comes from probability and statistics, the maximum likelihood estimation method. What we know so far is, given any simple linear regression model equation, we can estimate its parameter using ordinary least square estimation method, where we minimize the sum of squared errors and the value of the estimates is beta naught hat is equals to y bar minus beta 1 hat x bar. Beta 1 hat is equals to summation xi minus x bar times yi minus y bar divided by summation xi minus x bar whole square. And an estimate of sigma square hat is equals to SSE divided by n minus 2. And these are the value of the estimates we get when we use that method. But there is another fundamental question we can ask. What value of the parameters make the observed data most likely? And that leads us to maximum likelihood estimation method, a method rooted in probability and statistical inference. To apply maximum likelihood estimation method, we treat our data as coming from a probability distribution. So in any given simple linear model that looks like yi is equals to beta naught plus beta 1 xi plus epsilon I, where yi is the value of the dependent variable for the ith observation, xi is the value of the independent variable for the ith observation, and epsilon I accounts for the error term which we have from observation I. And given any data set, we would know the value of yi, we would know the value of xi, and the only unknown quantities we would have in the model equation are beta naught and beta 1. And we call these beta naught and beta 1 parameters. And so far we have learned that the first term, which is the combination of beta naught plus beta 1 xi, is called systematic component. And this epsilon I, which is the error term, is the random component. And because this epsilon I can take any value, we make some assumptions on this error term. These assumptions become the foundation for using maximum likelihood estimation method. Why? Because now we can write down a probability model for each observation using these assumptions. So we made these assumptions on the error term, that expectation of the error term we have from each observation is 0, variance of epsilon I is sigma square, all the EIs are independent and identically distribution and each I have normal distribution. We have also seen consequences of these assumptions on the dependent variable. And the consequence of the first assumption on the dependent variable is that expectation of yi is equals to beta naught plus beta 1 xi. The consequence of second assumption is that the variance of yi is sigma square for all I. And the consequence of the third assumption is that all yi's are also independent. And the fourth assumption is that the yi's are also normally distributed. And the consequences of these assumptions play a foundation role in the maximum likelihood estimation method. Let's look at the definition of the likelihood function first. The likelihood function represents the probability of observing our data set given specific values of the model parameters. Suppose n random variables x1, x2 till xn be a sample from a population with parameter theta. And this parameter theta is unknown. If x1, x2 till xn are the continuous random variable, then the likelihood function would be equals to the joint density function of these variable. And if all these variable are discrete random variable, then the likelihood function would be equals to the joint probability mass function of these random variable. So let's see what would be the likelihood function in the case of simple linear regression model. We would directly use the definition of the likelihood function and get that in the case of continuous random variables, the likelihood function becomes the joint probability density functions of the variables. And therefore, here the likelihood function would be equals to the joint probability density function of the responses. And mathematically, we would write it like this, that the likelihood function is equals to the joint probability density function of the dependent variable. So here, this f y1, y2 till yn denotes the joint probability density function of n dependent variable. So this is what we have using the definition of the likelihood function, that given n continuous random variable, then the likelihood function is equals to the joint density function. Now, one of the assumptions we have on the error term is that all EIs are independent. And as a consequence of this assumption, we would have that all YIs are also independent. And now, if all YIs are independent, then as a result, we can write the joint density function is equals to the product of their individual density function. So now we can write the joint density function f y1 y2 till yn is equals to product of the individual density function, product of the density function of each random variable, which is equals to the density function of y1 times the density function of y2 times the density function of y3, so on and so forth, the density function of yn. So we started with the definition of likelihood function, which we can write it as the joint density function. And using the consequence of the assumption that all yi's are now independent, because ei's are assumed to be independent, we can write this joint density function as the product of individual density function of yi's. Next, we have an assumption on error term that all ei's are normally distributed. And if all EIs are normally distributed, then as a consequence, we have that the dependent variable YIs are also normally distributed. And mathematically, we have that YI has normal distribution with mean beta naught plus beta 1 xi and variance sigma squared. And we have already seen this consequence of the assumption we have on error term. Now, if yi has normal distribution, then the density function of yi would be equals to 1 divided by square root 2 pi variance of that yi times e to the power minus yi minus mean whole square divided by twice variance. In the case of simple linear regression model, yi has mean beta naught plus beta 1 xi and variance sigma square. Therefore, the density function of yi would be equals to 1 divided by square root 2 pi sigma square times e to the power minus yi minus beta naught plus beta 1 xi whole square divided by 2 sigma square. And now we have the density function of yi. Since all yi are independent and identically distributed, we can use this density function in the definition of likelihood function. So we started with the definition of likelihood function, that it is equals to joint probability density function, which is further equals to the probability of the density function of each yi, which we get as a result of the consequence on the error term that all EIs are independent. And then we use the assumption that all EIs are normally distributed. And as a result, we have that all YIs also are normally distributed. And we have this equation. So now we have the product of the first term we have is square root 2 pi sigma square. It can also be written as 1 divided by 2 pi sigma square whole to the power 1 divided by 2. And we write the second term as it is. If we look at this term, we have product for the first term, which is 1 divided by 2 pi sigma square to the power 1 by 2. And we have this product for the second term as well. And therefore, we can rewrite this equation as product of the first term times the product of the second term. And therefore, we get product I going from 1 to n, 1 divided by 2 pi sigma square to the power 1 by 2 times product I going from 1 to n e to the power minus 1 divided by 2 sigma square times yi minus beta naught minus beta 1 xi whole square. Once we have simplified it till here, we use the fact that now the first term is 1 divided by 2 pi sigma square. Here, 2 is a fixed quantity, pi is a fixed quantity. If we look at sigma square, we do not know its value, but once we know its value, it will be a fixed quantity. It is not going to change if we move from one observation to another. Therefore, the first term we have over here is a fixed quantity, and we are multiplying this fixed quantity n times, and therefore the first term would become 1 divided by 2 pi sigma squared to the power n divided by 2. In the second term, we use one of the properties of the exponential function, which is product I going from 1 to n e to the power ai is equals to e to the power summation ai. And using that fact, we get that the second term is equals to e to the power summation I going from 1 to n minus 1 divided by 2 sigma square times yi minus beta naught minus beta 1 xi whole square. Let's simplify it further. On the left hand side, we have the likelihood function. The first term, we will write it as it is because we cannot simplify it any further. But if we look at the second term, we have exponential to the power summation of minus 1 divided by 2 sigma square, which is a fixed quantity. It is a constant. And we can pull it out of the summation sign. Therefore, we would have exponential to the power minus 1 divided by 2 sigma square times summation yi minus beta naught minus beta 1 xi whole square. And we have a simplified likelihood function value. And now, as the name suggests, maximum likelihood estimation method, we have the likelihood function. And now, in order to get an estimate of the parameter, we would maximize this function. And to maximize or minimize any function, we use basic calculus, where we find the derivative, set it equals to 0, and check if the function takes the maximum or minimum value at those points. So one of the ways to find maximum of this function is we can just directly take the derivative of this function. An easier way to approach this would be taking log both sides. So log is an increasing function, and maximizing this likelihood function would be equivalent to maximizing the log of this likelihood function to get the value of the estimates. So let's take log both sides. If we take log both sides, on the left hand side we have log of likelihood function, and on the right hand side we have log of this entire function. Inside log we have two terms. The first term is 1 divided by 2 pi sigma square whole to the power n by 2. And the second term is this exponential function. We use the property of logarithm function that log a times b is equals to log a plus b. Here we treat this first term as a, the second term exponential function as b, which is log of 1 divided by 2 pi sigma square to the power n by 2 plus log of this exponential function. And we can simplify it further by using another two properties of the log function. In the first term, we use the fact that log x to the power a is equals to a log x. So the quantity we have in the power comes to the front. And we have the first term is equals to n divided by 2 log 1 divided by 2 pi sigma square. And the second term would be just the quantity we have in the power of exponential function. Here we use the result that log e to the power x is equals to x. So we get log of exponential of this function to be equals to minus 1 divided by 2 sigma square summation yi minus beta naught minus beta 1 xi whole square. We can further simplify it by writing the first term log 1 divided by 2 pi sigma square as negative log 2 pi sigma square. And we write the second term as it is. Further, we treat this 2 pi as a, we treat the sigma square as b, and we have log a times b. This log a times b would become log a plus b, and therefore we have the first term negative n divided by 2 log 2 pi sigma square is equals to negative n divided by 2 log 2 pi minus n divided by 2 log sigma square. And we have simplified the log likelihood function. We cannot simplify it any further. So once we have simplified it, Now we can actually use the calculus to find the maximum of this log likelihood function. And how do we find the maximum of any function? We find the derivative of that function first and set it equals to 0. So now we will maximize this log likelihood function. We have three parameters over here, beta naught, beta 1 and sigma square. First, we take the partial derivative with respect to beta naught. When we take the partial derivative with respect to beta naught, the first term does not contain any term of beta naught, and we get 0 when we take the derivative with respect to beta naught. The second term, again, the derivative of this would with respect to beta naught would be 0. And the derivative of the third term with respect to beta naught would give us negative 1 divided by sigma square summation yi minus beta naught minus beta 1 xi. Next, we find the partial derivative of this log likelihood function with respect to beta 1. And the partial derivative of the first term with respect to beta 1 would be 0. The derivative of the second term with respect to beta 1 would be 0. And the derivative of the third term with respect to beta 1 would give us this value. And next, we find the derivative of this log likelihood function with respect to sigma square. The partial derivative of the first term with respect to sigma square would be 0. The partial derivative of the second term with respect to sigma square would give us negative n divided by 2. And the derivative of log sigma square would be 1 divided by sigma square. And we get the remaining term when we take the partial derivative of the third term in the log likelihood function with respect to sigma square. The next thing would be to set these partial derivatives with respect to each parameter equals to 0, because that would give us the critical points, and those critical points would serve as an estimates of the parameters. So we set the derivative of the log likelihood function with respect to beta naught equals to 0. And we get summation yi minus beta naught minus beta 1 xi is equals to 0. And if you remember, when we used ordinary least square estimation method where we minimize the sum of squared error, we got exactly this equation over there. So we use the same steps as we used in ordinary least square estimation method, and we get an estimate of beta naught is equals to y bar minus beta 1 tilde x bar. Now remember, this tilde over here means that it is an estimate of beta naught, but this tilde means that it is a maximum likelihood estimate of beta naught. And we put a hat over the parameter when it is an ordinary least square estimate. So an estimate of beta naught using maximum likelihood method is exactly the same as the estimate we get using ordinary least square estimation method. Next, we set the partial derivative of log likelihood function with respect to beta 1 is equals to 0. When we do that, we get summation yi minus beta naught minus beta 1 xi times xi is equals to 0. And again, what we get is exactly the same as what we got when we used the ordinary least square estimation method. So we imitate the steps from there, and we get that the maximum likelihood estimate of beta 1 is exactly the same as what we get when we use ordinary least square estimation method. And this beta 1 tilde here denotes the maximum likelihood estimate of beta 1, which is equals to summation yi minus y bar times xi minus x bar divided by summation xi minus x bar whole square. So we have estimates of both beta naught and beta 1. We still need to find an estimate of sigma square. Therefore, we set the partial derivative of log likelihood function with respect to sigma square is equals to 0. When we set it equals to 0, this is what we get. Negative n divided by 2 sigma square plus 1 divided by 2 sigma to the power 4 summation yi minus beta naught minus beta 1 xi whole square is equals to 0. And we have the maximum likelihood estimate of sigma square is equals to SSE divided by n. And we denote this estimate by sigma square tilde. Note that when we used ordinary least square estimation method, we were not able to obtain this estimate directly. But when we use this maximum likelihood estimation method, we directly get an estimate of sigma square. And here we have the estimates of all the parameters for the simple linear regression model using maximum likelihood estimation method. And we are going to talk about the similarities and the differences between the estimates we have using both the methods we have seen so far in the next video.